part of the homework. So, yeah, also homework 7 and 8 were checked, but it was okay, I think. Yeah. Yes, I think you solved it. Yes, yeah. Number 9 was more problematic. So we considered homework. We considered the Klein quartic, which is the set of points x, y, q plus y, z, q plus z, x cube equals 0 in CP2. So the genius is equal to 3. And actually, the main point of this homework, the goal was to prove that the automorphism group of X has order 168, which is maximal possible for G equals 3. We know that it cannot be more than 84 times G minus 1, but so this is exactly the maximum. Okay, and then basically in this homework there was some strategy. There was some strategy was proposed. How to prove it? So basically, yes. Yeah, but then, of course, I mean there is a simple homomorphism, simple automorphism, X of this guy. Yeah. There's also a bit more interesting. So this can go to zeta x y for z, where zeta is the 7th root of unity. So there is an obvious automorphism of X. There is maybe not immediately obvious, but simple. But there is also the much more interesting automorphism. X, Y, Z goes to this matrix. But let us denote it actually in this way: omega. It has this form: omega 2, omega 3. And then you shift it, yes, up. Yeah. So omega 2, omega 1. Again up. Omega 3, omega 1. Times x, y, z. Where omega 1 is zeta squared minus zeta minus 2, omega 2 is equal to yes. Yeah. Then okay. Then how to check? How to check that this is an automorphism? Yeah? Which is looks very non-trivial. Actually, I don't know how to come to this automorphism. It's quite non-trivial. But okay, since our goal is just to check that this is an automorphism. Okay, but then I suggest just to, yeah, you just substitute, you just make a direct substitution. Yeah, so you just, okay, let us denote by f x, y, z. Yeah, actually, just this polynomial. Yeah? Let us denote it just by p. This polynomial by p. X, y, z. Yes, and then yes, and okay, and then and this transformation, let us denote it by, I don't know, sigma sigma x, y, z. Yeah, and then basically how to check. Let us check that if you apply sigma and compute p, then you again get some constant times p. Yeah, clear. This is enough. Yeah. Okay. Yeah. Then okay. I just suggest, yeah, first to use symmetry. Yeah. So what you have this. Yeah. You have. Okay. Let us denote this guy. I don't know. Tau of x, y, z. Just the shift. The cyclic shift, yeah, x, y, z. Yes. Yeah, but yeah. Then you just note that this guy satisfies. So if you apply tau sigma tau, then you get sigma. Yes. Okay. Yeah, and then, yeah, this is simple. Yeah, then you also note that p, this p of tau x, y, z is equal to p x. Yeah, obviously, if you make a cyclic permutation of these variables, then p is the same. Yeah, so basically, I just want first I want to say that if you now write p of sigma tau x, y, z, then this is equal to what, p tau inverse x sigma applied x, y, z. Okay, and then this is equal to p sigma x. Okay, and then basically this implies that this polynomial that we want to compute, p x p sigma x, y, z, is equal to what? Is equal to some constant alpha, and then you have this xy cube plus cyclic permutations. Yeah, just I want to write all invariant polynomials under cyclic permutations. Yeah? So what we can have? We can have such a guy, which is actually p, yeah? Plus beta, and then okay, you can have xy squared plus cyclic permutations plus gamma x cube y plus cyclic permutations plus delta x to the power 4 plus cyclic permutations plus what? Yeah, plus beta gamma delta eta x y squared z plus cyclic permutations. Yeah. Yes. So this means that we just have to check that the coefficients of these monomials are 0. Yeah. And do you want to say that it's very complicated? What do you want to check? What coefficient do you want to check? Okay. What do you want? Yeah, x. Yeah, он здесь будет. Indeed, there are two types: xy cube or x cube y plus cyclic. So I see that you came also to this point, but okay. Then what coefficient do you want to check? This one. But alpha, we don't need alpha, yes? But it can be 0 also. Yeah, it cannot be 0 because otherwise this map is non-degenerate. Yeah. I mean, this is because these guys are pairwise distinct, yes? So you have to check the vanishing of these 4 guys. And you say, okay, you want to try gamma, yes? So we want to compute basically coefficient of x cube y of p sigma x y z. So yes. Okay. Okay, you're right. Okay, you're right. You write this expression: coefficient x cube y. Okay, then big sum x omega 1x plus omega 2y plus omega 3z y cube. Yes, omega 2x plus omega 3. But yeah, we can forget about z, yes? Yeah. Because we don't need it, yes? We don't need z. Yes, omega 2, omega 3 y cube plus y z cube omega 2x z cube omega 3x plus omega 1 plus z omega 3 omega 1 y x cube omega 1x. Okay. Okay, so we want to extract x cube y from here. Okay, you can take x from here, yes, and then you get 1, omega 1, x squared y from here. Yes, so x squared y from here. So then you get 3 omega square omega 3. Or you can take y from here and x cubed from here. Huh? Omega 3, yes. Or you can take y from here, omega 2, and x cubed from here, omega 2 cube. Okay. Huh? Ah, yes. Plus. А? Да? Думаете? Да, так и получается? Ну нет, ну почему? То есть омега. Нет, с циклическими перестановками омега-1, омега-2 и омега-3, да? Да. Ну да. Ну, okay. So indeed, then you can easily compute all other terms just by permutation, just by cyclic permutations of omegas. Yeah. So here then you get omega 2, omega 1 squared, omega. Oh no, omega 3 squared, omega 1 plus omega 3 to the power 4. And here you get 2, 3, 1, and omega 3 plus omega 1, omega 1 squared, omega 2 plus omega 1 to the power 4. Yes. And then you just have to substitute. Yeah, but no, I think one can do something here. Okay, so first of all, then one gets 3 omega 1, omega 2, omega 3. And here you get the sum, omega 1, omega 2, omega 3. Yes. But this is actually should be simple, yes, because some of these, but no. Ну, понятно, что если все подставить сюда, да, ну, получится многочлен Лорана от КСИ. Да. Ну, ладно. Хорошо. Ну, наверное, не будем все-таки отвлекаться на это. Да, ну, возможно, действительно, да. То есть это как бы получается прямая проверка. Не, ну это точно верно, я проверил на компьютере. Вот. Ну, возможно, да, для ручного счета это как бы тяжеловато. Хорошо. Ну ладно, тогда пусть будет вам полный балл тогда. Тогда вам странно снижать. Ладно, хорошо. Okay, so we agreed that possibly this is a quite complicated computation. It was not so good from my side. Yeah, of course. I mean, yeah. Of course, I checked it on computer, but indeed by hand. Yeah. Okay. Yes. Then? Yeah. Then all other steps. Yeah, you did correctly. Okay. Then we have to finish the proof of Hurwitz's theorem. Yes. So we have this, and we have to check that the number of automorphisms is less or equal than proof. We considered the projection from X to X quotient by G. And then what we did, G, let us denote by G the automorphism group. Yes, then in the previous lecture we showed that this is a compact Riemann surface. And then Y. Yes, and then we considered several cases. So we considered the case. Yeah. So what we did, we then showed that the number of elements in G is equal to G minus 1 2 times 2G of Y minus 2 plus sum over the critical points by 1 minus 1 over M of Y. Where what is M of Y? So we so if here we have a Y, then here we have some point. Then if we consider the preimage, then we can choose some point X. Then M of Y is by definition the number of the elements in the stabilizer of this point X. Yes. And then we discussed that this number doesn't depend on the choice of the point, because the orders of the stabilizers of the points in the same G orbit are the same. Okay, and then we got this formula, the main formula. Yes, and then we considered several cases. So we considered case 1, G of Y equal to 2. So it was done. Then we considered case 2, g of y is equal to 1, yeah, but maybe actually it's good. So to write. So in this case, we immediately got that this guy is less or equal than g minus 1, and in this case, we got that is less or equal than 4g minus 1. Yes, and then we have the remaining case when g of y is equal to 0. And this we have to do now. Yes? Yes, and then there was some, we had exercise. We had some exercise saying that if we have a non-constant holomorphic map from a Riemann surface of genius at least 1 to CP1, then the number of critical points is at least 3. So in the spring semester, we had an exercise saying that the number of the critical points is greater or equal to 3. Yes, and then again we have several cases. Okay, case 3a. Case 3a. Suppose that the number of the critical points is greater or equal than 5. Okay, then we write the denominator. Yes, so we now, since we want to find the maximum of this guy, we have to find the minimum of the denominator. Yes, so the denominator is minus 2 plus sum over the critical points 1 minus m of y. So we know which is minus 2 plus, we know that, so this is greater or equal, minus 2 plus, we know that there are at least 5 critical points. Okay, we suppose there are at least 5 critical points. So plus 5 times, and how to bound from below this guy? 1/2, yes. Plus 1/2, yeah, because m of y greater or equal to 2, yeah, if I is a critical points. Yes, so, and then this is equal to 1/2. So, and then in this case, what is the bound for the order of the automorphism group? No. Yeah, 4g minus 1, because here we have 2, and we get the minimum 1/2 for the denominator. So we get 4g minus 1. Okay, and then we continue in the same way. But I suggest to follow carefully all the arguments, because there will be some further homework for which you will need to understand the proof very well. Case 4b, the number of the critical point is exactly 4. Okay, then we write minus 2 plus sum (1 minus 1). So here you have exactly 4 summons. So you can write that this is equal to 2 minus sum over the critical points 1 over m of y. But then you can just try to find the minimum as follows. So this is the minimum of these guys. 2, 1a minus 1b minus 1c minus 1d. So you have 4 points, exactly 4 points. Oh, sorry, why do I write it like this? You have 4 points. You want to find the minimum. But as I said on the last lecture, this denominator have to be positive. So it cannot be 0 or negative. Yeah? This follows from the Riemann-Hurwitz formula. So you are allowed only such, okay, you have one restriction, this m of y greater or equal to 2. But you have another restriction that this sum should be positive. So you have, so this guy is greater or equal than the minimum of all such expressions where this expression is positive. And of course, A, B, C, D. So in particular, probably you could think that you can write A equals B equals B equals C equals D equals 2, but then you get 0, which is not allowed. So then what is the minimum of these? What is the minimum of this expression under such conditions? Yeah. So indeed, the first guess is when all of them are 2, but then this guy is 0, and then the next one is obviously when you have 1/2, 1/2, 1/2, 1/3, which is equal to 1/2 minus 1/3 is equal to 1/6. And then this implies that in this case the order of the automorphism group is less or equal than 12g minus 1. Yes. Okay, and then we have the most interesting case. Yes, the case 3c, when the number of critical points is exactly 3. Okay, then you have to write then minus 2 plus sum 1 minus 1 m of y. So you have here 3 summands. And then you get 1 minus sum 1 over m of y. So and again, you want to find the minimum. Substituting instead of m of y arbitrary numbers greater or equal to 2, such that this guy is positive. Yeah? So this is the minimum. 1 minus 1a minus 1b minus 1c, and here you have minus 1a minus 1b minus 1c a. And of course, you can assume that, for example, A greater or equal to B, greater or equal to C, greater or equal to 2. Okay, and then what you do, you and then you just consider several cases, again, 3 cases. The first case is when C is greater or equal to 3. Yes, then the minimum is so now you want to find the minimum when you have one more condition, that C is greater or equal to 3. And what is then the minimum? No, this is not good, because then this is 0. Yes. So you get 1 minus 1 3 minus 1 3 minus 1 4, and then it is equal to 1 over 3 minus 1 over 4 is equal to 1 over 12. So in this case, the order of the automorphism group is less or equal than 24 G minus 1. So you see we are getting closer and closer. Then the second case is when C equals 2 and B greater or equal to 4. Okay, then what is the minimum in this case? Yes. So minus 1 over 2 minus 1 over 4. Yeah, then I mean, the naive guess would be to try again 1 over 4, but then you get 0. And then the next one gives you the minimum. So so this is 1 over 4 minus 1 over 5, which is equal to 1 over 20. So in this case, the number of the automorphism group is less or equal than 40 G minus 1. And finally, the last case. The last case. 3. C equals 2. Yeah, then if C is equal to 2, B cannot be equal to 2, yes? Because if C is equal to 2, B cannot be equal to 2, because then the sum is 0 or negative, yes? So B should be greater or equal to 3. The case B greater or equal to 4 is done. So remaining case is when B is equal to 3. So B equals 3. Okay, then you just have to find the minimum of these expressions. 1 minus 1a minus 1 over 3 minus 1 over 2. This is equal to 1/6 minus 1a. And then you have to have the condition -6 minus 1a is greater than 0. Yeah. And then, okay, the minimum is obtained when a is equal to 7, the next number after 6. So 1/6 minus 1/7, 1 over 42. Yes, and then in this case is 84 G minus 1. Yes, this is done. Any questions? No. Yeah, then you will have I have a very good homework for you without such big computations. Now, I will tell you. I will tell you now because it's an interesting fact that. So, of course, I will send you. But okay, the first proof the fact is the following. Suppose the genus is greater or equal to 2, and the number of automorphisms is less than 84 g minus 1. So the maximum is not achieved. Then the number of automorphisms is less or equal than 84 g minus 1. So you see, it's not like any number before this guy can be achieved. It drops. There is some, how to say, скачки. Как скачки по-английски? Скачок. Okay. Yeah, some gaps. Yeah, some gaps. Indeed. Yeah, so this will be the first one. And then the second fact is that in Genius 2 you obtain exactly like this. So if G is equal to 2, then you have exactly this case. Then is less or equal than 84. Not 48. So you see, in Genius 2, you don't have maximum possible number, but you have the next one. And the third one is, again, there is a very nice surface. It's called Boltza surface, but I don't remember how to write it in English. Okay, поверхность Больца. It's a hyperelliptic Riemann surface that is obtained by the compactification of the surface given by y squared is equal to x to the power 5 minus x Yeah, we discussed in the spring course that if you have usually you can obtain hyperelliptic curves by considering y squared equals some even polynomial, but you can also by adding 2 points. But if you consider y squared equals to some polynomial of degree of odd degree, then by adding 1 more point you can obtain a compact Riemann surface. Okay, and then this guy has exactly this number of automorphisms. So it has genius 2 and the number of automorphisms is exactly 48. But this is much easier than this Klein quartic. Boltza. Maybe you can, I didn't take my phone. Maybe you can have an English, or you can find, search how to write it in English. Надо просто в Яндексе там набрать этот поверхность Больца. И все, оно выдаст там Википедию на английском сразу. It's a name, yes, of some guy. Boltza surface, yes. Okay, it was obvious. Boltza surface. Yeah, some scientist. Okay. So this is all. Нет, это сейчас. Нет, это не очевидно, нет. Ну, я подсказки дам, как это проделать.
В этой части второй пункт это просто очевидное следствие первого пункта или там что-то большее?
Вот это? Не понял. Вот это. Надо доказать, if you know the first point, then in order to prove the second, you should just prove that you cannot have the automorphism group of order 84. So basically this is equivalent to saying that the automorphism group cannot be equal to 84. В первом мы предполагаем, что максимум не достигается, тогда он резко падает обязательно до вот этого числа. Да. Ну, собственно, тогда во втором пункте надо просто доказать, что 84 не достигается. No, why? Oh, here you suppose that automorphism is less than 84 G minus 1. Then it's automatically less or equal than this guy. Yeah. So you see, here we saw something. For example, here you see, in all the cases that we considered, we got less or equal to 24, 40. But somewhere there is number 48. Huh? Ну да. Okay, yeah, it's not hard. Okay. Yeah, but and then actually, yeah, okay. No, but maybe I can say, yeah, indeed. The next, so after, so G equals 3. So if so genera when this bound is achieved. So as I explained you, this bound so is not achieved in Genius 2. This is the homework. Then it's achieved in Genius 3. It was the previous homework. But then there is some sequence of numbers, some sequence of genera where it is achieved. So the first is 3, then 7, then so some strange numbers. So here we have Klein quartic, and here there is some surface called Macbeth surface. Yeah. So when the automorphism group is equal to 84 times 6. Yeah. Okay. So there are some nice, beautiful examples here. Yes, but then we continue. Yeah, we have to now to discuss Abel's theorem. This will occupy the remaining part of the course. Yes, but first we will discuss harmonic differential forms. Okay. Harmonic differential yes. So in the case of Riemann surfaces, it is quite simple. So what we have, so if suppose X some Riemann surface, then and okay, suppose we have some open set and some smooth differential form. So then, then we have omega bar, yeah, form. Yeah, I mean just complex conjugation. Yes, so if omega, you for example can write omega as f1 dx plus f2 dy. Yeah, then omega is just f1 bar dx plus f2 bar dy. Or you can use a complex coordinate. So x. So you have some complex coordinate. Yeah, and it's real and imaginary part. Or you can use h1 dz plus dz bar. Yeah, and then this is of course equal to h1 bar dz bar plus h2 bar dz. Okay, so obvious operation. Yes. Yeah, then you have this star operation. So omega you can write omega 1 plus omega 2. You can any differential form you can decompose as a sum of the form of type 1, 0. Sorry, it's on U. Yeah, so. And this guy belongs to omega 0, 1 of U. Yeah, so any smooth form can be written as a sum of a form of type 1, 0 and the form of type 0, 1. And then the main definition is here star omega is equal to I minus omega we have this star operation. Yeah, and then we have some easy properties. So lemma. Sorry, again it's on U, yes, not necessarily. Yeah, but we can have on X, of course. Doesn't matter. Okay, what we have. Yes, yeah. So, that's right, indeed, to recall that. This is omega 1 is, it's h1 dz, yeah? So basically, this is omega 1 locally. This is omega 2. Yeah, so you have the star operation, and then there are various simple properties. The first one says that star omega is equal to minus omega, and star omega bar is equal to star omega bar. Yes. D star omega is equal to I d prime omega 1 bar minus I omega 2 bar. So suppose you have also some function, some smooth function. Then star d prime f is equal to I d double prime d minus I d prime f. F is equal to 2I d prime okay, some various properties, some properties. Yes, so yeah, but yeah, basically it's just direct computation. Yeah, so for example, 1. So what you have? Star omega. Yeah, star. For example, star omega. Star. And here you write the definition. Yes. And you write here minus I omega 2 bar plus I omega 1 bar. Yeah, then now this guy is from epsilon 1 0 of u. Then if you apply star again, then it will be I, this guy bar, so I omega 1 without bar minus bar of this, so plus I omega 1, so will be minus omega 1 plus omega 2, so equals minus omega. Yeah, d prime f is df dz dz, and d prime d double prime f is df dz bar dz bar. Huh? Формул. Ну тоже the same, so you so you have, for example, d prime of f1 dz plus f2 dz bar. Since d prime produces dz, it annihilates the first one, so it acts non-trivially only on the second one. So it's df2 dz wedge dz bar. Yeah, and d double prime is the same. Yes, basically, yeah, I mean, it's a bit, it's a direct simple computation. I mean, you can choose some equation that you want to check.
Or I have a question, because dz bar is not the same as dz bar. I mean, with the bar over.
No, it's the same. Yeah, yeah. But okay, let us. I can recall, of course. Yeah. So what is, for example, d over dz is 1/2 d dx minus I dy d dx plus I dy. Yeah, and then of course dz is dx plus I dy, and dz bar is dx minus I dy. Yeah, and then of course it's equal to dz bar. Yes, okay. Yeah, okay, we can check something. I don't know. First part of 3, example. The first, for example, 3.
Yes, I was thinking like already to operations on vector tangent vectors would be the same, like because it would be applying only in the base, like in the partial of quantity. Yeah, like there's the base. That one is the partials of C, Z, and Z conjugate.
Yes.
But our form here, dz, it only applies to the part of partial of Z, and the conjugate only the part of partial of Z conjugate.
Yeah, yeah.
So this one, it would be like we have to say that one, like dz bar is the same as the Z conjugate.
Uh-huh. Yeah, for example, yeah, this star d prime f is star df dz. Then you apply I this bar, so you get df bar, dz bar, dz bar. And then this is equal to I d double prime f bar. So the same. And then, for example, we can check 4. Yeah, so d star df is d star df star d prime f plus star d double prime f. Then you apply the first part of number 3. So it's I d double prime f bar minus I d prime f bar. Yes, and then when you act d to d double prime produces dz bar. So only d prime can act here. Yeah? So you can write I d prime d double prime f bar, and here by the same reasons minus I d double prime d prime f bar. And of course they anti-commute these d prime and d double prime, so you then get 2I d prime d double prime f bar. Yes. Okay. Yeah, then all other parts are easy, so I leave them as an exercise. Any questions? Okay. Yeah, then we have the next simple definition. Also, we have a definition of anti-holomorphic form. Yeah, so, if omega is a holomorphic form, then omega bar is called anti-holomorphic. Anti-holomorphic. And then the space, so anti-holomorphic form is denoted by this. So it's basically omega bar so it's a subspace in the space of all smooth forms of on U. It's called anti-holomorphic. Yes. So and the space is denoted in this way. Yes, and then the next definition. Omega, a smooth form, is called harmonic. If d omega equals d star omega equals 0. Yes. Yeah, and then the next lemma says that harmonic forms are precisely sums of holomorphic and anti-holomorphic forms. We have the next simple lemma. Saying that omega is harmonic. It's equivalent to the fact that d prime omega equals d double prime omega equals 0. And this is equivalent to the fact that omega is equal to omega 1, omega 1 plus omega 2, where omega 1 where this guy is holomorphic and this guy is anti-holomorphic. Yes. And then the proof is easy. So you just check. You write omega. Yeah, where this is a form of type 1, 0. This is a form of type 0, 1. Yeah, so then dy, d omega is equal to, so if you want to compute d omega, then you can, to omega 1, you can apply only d double prime. So d double prime omega 1 plus d prime omega 2. And then if you want to apply star, d star omega, then this is d I omega 1 minus I and then you have I you can write d double prime omega 1 minus d prime omega 2 bar. Yes. So basically, the form is harmonic if these two guys are 0. So meaning that these two expressions are 0. So omega is harmonic. Is equivalent to the fact that d prime omega, d double prime omega 1 plus d prime omega 2 equals 0, and the difference. Yeah, which is of course equivalent to the fact that d double prime omega 1 equals 0 equals d prime omega 2. But this is of course equal to d double prime omega, and this is equal to d prime omega. So the first equivalence is proved. Yeah, and the second one is also obvious, yes, because this inequality is equivalent. This equality is equivalent to saying that omega 1 is holomorphic, and the first equality is equivalent to saying that omega 2 is anti-holomorphic. Okay, so this is done. Any questions? No. Okay. Yes, then here we have the notation. So notation. So the space of harmonic one forms. So is the sum of holomorphic. So U plus anti-holomorphic. So the space of holomorphic harmonic one forms is denoted by this one. Then if X is compact, then we know that the dimension of holomorphic one forms on X is equal to G. So we get that the dimension of the space of harmonic forms on X is equal to 2G. So the space of harmonic one forms, harmonic forms on a compact Riemann surface of genus G is equal to 2G. Yes, there is then the space of smooth one forms on a compact Riemann surface is endowed with a scalar product. So now we assume that X is a compact. Riemann surface. Then if we have two forms. Two smooth forms, then we define this, the following scalar product. You compute the integral over x of omega 1 wedge omega wedge star omega 2. Yeah, so obviously it satisfies it's linear with respect to the first argument. And we have the following relation for the second. Yes. Yeah. Then, yeah. I just want now to check that it's a Hermitian scalar product. Then let us also check. Yeah, then let us check that positive definite. Yeah. Let us compute omega omega. Yeah. So it's an integral over x. Omega wedge star omega. Okay, then you compute. Actually, we have to finish it already. Then we compute. Yeah, so if omega is equal to f dz plus g dz bar, then star omega is equal to I f bar dz bar minus I g bar dz. Yeah, then omega wedge star omega is equal to I f bar plus I g bar dz bar, and this guy is equal to what? To minus 2I dx dy. Yeah, so this is equal to twice dx dy. So, and this is a non-negative, real and non-negative. So belongs to and omega if and only if omega equals to 0. Indeed, it's a scalar product. So this is a scalar product on the space of smooth one forms on a compact Riemann surface. Yes. Okay, so we have to finish. Then we will continue in the next lecture. Хороший вопрос. Нет, я не знаю. Ну да, тут еще звездочка Ходжа есть. Нет, я что-то не знаю. Так, вот здесь это то же самое должно быть. Но там силометрика. Да. Ну ладно. Можно попробовать выяснить.